Imagine holding a chunk of rust-colored rock in your hand. It is cold, it is brittle, and it looks about as useful as a doorstop. Now imagine throwing that rock into a furnace so hot that the air inside glows white. A furnace tall enough to dwarf a 10-story building, burning so furiously that the ground around it trembles. 6 hours later, that worthless-looking rock has become a river of glowing liquid metal, pouring out of a tap hole at nearly 3,000 degrees Fahrenheit in a spray of sparks that lights up the night sky like a fallen sun. That is what a blast furnace does. It takes mountains of dead rock and turns them into the liquid iron that built every bridge, every skyscraper, every railroad, and every warship that made the United States what it is. Without this machine, there are no steel beams holding up Manhattan. There are no transcontinental railroads crossing the Great Plains. There are no battleships rolling off the ways at the Brooklyn Navy Yard. But the story of how America figured out this trick and then scaled it up until it was producing more iron than every other country on Earth combined is one of the wildest industrial stories ever told. It starts in 1646 on the muddy banks of a river in Massachusetts that most people have never heard of. The Saugus River. The Puritan settlers of the Massachusetts Bay Colony had a problem. They needed iron. Axes to clear forests, nails to frame houses, hoes to break soil, pots to cook meals. They had been hauling all of it across the Atlantic from England, and that was slow and expensive. So a group of English investors called the Company of Undertakers decided to build an ironworks right here in the colony. They hired a merchant named Richard Leader who knew the smelting process. And Leader picked a spot along the Saugus River in what is now Saugus, Massachusetts. The river had a fast current to power water wheels. The surrounding forests could be burned down into charcoal for fuel, and the nearby swamps and ponds held deposits of bog ore, an iron-rich muck called limonite that could be dug right out of the ground. Leader built the whole operation from scratch. A blast furnace for smelting ore into pig iron, a forge for hammering that pig iron into wrought iron bars, a rolling mill, a slitting mill, even a 500-pound drop hammer. This was not some backyard experiment. The Saugus Iron Works, which they called Hammersmith, was a full-scale integrated industrial facility, the first of its kind anywhere in North America. And it used technology every bit as advanced as anything operating in Europe at the time. The process was brutal and simple, and it would have been terrifying to watch up close. Workers loaded the top of the stone furnace with alternating layers of charcoal and iron ore. Massive bellows, driven by the river's water wheels through a system of huge wooden gears, forced air into the bottom of the furnace to make the charcoal burn hotter. The furnace roared. Sparks shot from the stack. The heat near the base was intense enough to blister exposed skin in seconds. At those temperatures, the carbon in the charcoal reacted with the oxygen locked inside the iron ore, pulling it away and leaving behind crude molten iron that pooled at the base of the furnace. Workers would tap that iron into molds on the sand floor of the casting house, where the metal ran into channels that branched off a central trench. The shapes looked like piglets nursing from a sow, and that is exactly where the term pig iron comes from. Some of the molten iron went directly into cast molds to produce finished goods right there on the spot. Things like firebacks for hearths, cooking pots, kettles, and skillets. The rest was refined into wrought iron at the forge next door, where workers hammered the pig iron under that 500-pound drop hammer to drive out impurities and shape it into merchant bars, which were then sold to blacksmiths across the colony. The Saugus Works ran for about 25 years, producing iron for the colony and even exporting some back to England. But it was plagued by lawsuits, money troubles, and a chronic shortage of skilled labor. By the early 1670s, the furnaces had gone cold and the buildings were abandoned. The site was eventually swallowed by brush and forgotten for nearly 300 years, until archaeologists dug it up in 1948. Today, it is a National Historic Site, and the National Park Service calls it the first chapter in America's industrial story. But here is the thing. That colonial furnace at Saugus, as impressive as it was for its time, produced a trickle of iron compared to what was coming. Because to understand why America eventually crushed every other iron-producing nation on Earth, you have to understand what actually happens inside a blast furnace. Not the simplified version, the real version. A blast furnace is a giant vertical shaft built from steel plates and lined on the inside with heat-resistant brick. Modern ones stand over 100 feet tall with hearth diameters of 20 to 50 feet across. You feed three things into the top: iron ore, which arrives as marble-sized pellets containing 60 to 65% iron; coke, which is coal that has been baked in an oven to drive off impurities and turn it into nearly pure carbon; and limestone, which acts as a chemical cleaning agent called flux. These three materials, collectively called the burden, descend slowly through the furnace under their own weight. Meanwhile, from the bottom, a blast of air preheated to somewhere between 900 and 1300 degrees Celsius is forced in through a ring of water-cooled copper nozzles called tuyères. That is where the name blast furnace comes from. The blast. When that superheated air hits the coke at the bottom of the furnace, the temperature in the combustion zone spikes to between 1800 and 2200 degrees Celsius. The coke ignites and reacts with the oxygen in the blast to produce carbon dioxide. But the furnace is so hot and so packed with carbon that the carbon dioxide immediately reacts with more coke and converts into carbon monoxide gas. This is the critical moment. That carbon monoxide is the real workhorse of the entire process. It rises through the descending column of ore, and as it climbs, it strips the oxygen atoms away from the iron oxide in the ore. This is the chemical reduction reaction that transforms rock into metal. The oxygen leaves with the carbon monoxide, exiting through the top of the furnace as waste gas. And what is left behind is iron. At first, the reduced iron is still solid, a spongy mass working its way down through the hotter and hotter zones of the furnace. In the upper shaft, where temperatures sit between 400 and 800 degrees Celsius, the indirect reduction zone does most of the chemical work. The rising carbon monoxide gas passes through the descending ore pellets, and the iron oxide goes through a series of stepwise transformations, from hematite to magnetite to wustite, and finally to metallic iron. Each step strips away more oxygen, but the iron is still solid here. It has not melted yet. As the reduced ore continues to descend past the 800-degree mark and keeps dropping toward the combustion zone, carbon from the coke begins dissolving into it, which lowers the iron's melting point. The solid sponge softens, begins to drip, and eventually liquefies completely, trickling down through the remaining coke to pool at the very bottom of the furnace in a basin called the hearth. At the same time, the limestone has been going through its own transformation. The heat decomposes it into calcium oxide, which reacts with impurities in the ore, things like silica and alumina and sulfur, and binds them into a glassy waste material called slag. The slag is lighter than liquid iron, so it floats on top like oil on water. Workers tap the slag and the iron through separate tap holes at different heights in the hearth, and the two materials flow out in separate channels. The molten iron, glowing orange-white and throwing off waves of heat that you can feel from 50 feet away, runs into ladles or torpedo-shaped rail cars for transport to steel-making furnaces. The entire process, from raw materials dumped in at the top to liquid iron tapped at the bottom, takes roughly 6 to 8 hours. And here is the part that catches most people off guard. A blast furnace never stops. Once it is lit, it runs continuously, 24 hours a day, 7 days a week, for 10 to 20 years straight, before it needs to be shut down and rebuilt from the inside. There is no off switch. There is no weekend. Christmas morning, the furnace is running. A hurricane rolls through, and the furnace is still running. The entire operation is staffed in rotating shifts around the clock because the chemistry inside the furnace depends on maintaining a steady state of temperature and material flow. If you interrupt that flow, the molten iron inside the hearth can begin to solidify, the burden above it can bridge and lock up, and the whole thing can turn into a frozen mass of metal and rock that is almost impossible to remove. Shutting one down early, even for a few days, risks a catastrophic freeze-up that can destroy the furnace lining and cost tens of millions of dollars. So that is the machine, a continuously running countercurrent chemical reactor that eats rock and breathes fire and bleeds liquid iron from its base every few hours. And what America figured out in the second half of the 1800s was how to scale this machine up to a size and speed that nobody else in the world could match. The critical ingredient was ore. You can build the biggest furnace in the world, but without a reliable, massive supply of iron ore, it is just an expensive chimney. And in 1890, a family from northeastern Minnesota found the biggest deposit of iron ore the United States had ever seen. The Merritt brothers, led by Leonidas Merritt, had been prospecting the thick forests and swamps of the Mesabi Range for years, looking for iron. Their father Lewis had believed ore was buried somewhere under that ground, but he died in 1880 without ever proving it. His sons, all 7 of them, kept searching. They endured freezing winters, mosquito-choked summers, and years of disappointment, while other prospectors called them dreamers. Then, in November of 1890, a mining captain named J.A. Nichols, working for the Merritts, sank a test pit near what is now Mountain Iron, Minnesota, and struck a massive iron deposit just a few feet below the surface. The next day, Nichols delivered 50 pounds of the stuff, a rich, marvelous sample testing at around 64% iron. The ore was soft hematite, powdery and reddish, not the hard crystalline rock that miners in other regions were used to. That softness had actually delayed the discovery for years, because prospectors kept walking over it without recognizing what they were standing on. The Merritts expanded their holdings fast, eventually grabbing as many as 141 leases across the range. They opened their Mountain Iron mine and began shipping ore in 1892, but the Merritts had a problem that was about to swallow them whole. They had ore, but no capital. Moving that ore from the forests of northeastern Minnesota to the blast furnaces in Pennsylvania, Ohio, and Illinois required railroads to haul it overland and ore docks on Lake Superior to load it onto Great Lakes freighters for the journey east. Building that infrastructure cost money the Merritts did not have. So they turned to John D. Rockefeller, the oil baron, who was always looking for the next big play. Rockefeller loaned them cash in exchange for company stock. When the financial panic of 1893 slammed the national economy, the Merritts could not repay their debts. Rockefeller took control of their mines. The family that discovered the richest iron deposit in American history, a deposit that would eventually yield more than 3 billion tons of ore, was pushed out of the industry entirely. It is one of the cruelest ironies in the history of American business. Meanwhile, a Pittsburgh businessman named Henry Oliver had traveled to the Mesabi Range and seen the potential. He bought one of the ore deposits for $75,000 and 65 cents per ton of ore mined. But Oliver had his own cash problems. He needed a partner with deep pockets and, more importantly, someone who actually owned blast furnaces. He went to Andrew Carnegie. Carnegie initially thought ore mining was a money-losing business, but his right-hand man, Henry Clay Frick, saw the opportunity and pushed Carnegie to take the deal. In 1894, Carnegie loaned Oliver $500,000 in exchange for half of Oliver's mining company's stock. Now Carnegie had his own ore supply feeding his Pittsburgh blast furnaces directly. Rockefeller had ore too, but no blast furnaces to process it. He had no choice but to sell to Carnegie. So the 3 men cut a deal in 1896 that carved up the entire supply chain. Oliver would mine the ore. Rockefeller's railroads would haul it to the docks. Carnegie's blast furnaces in Pittsburgh would turn it into iron and steel. It was vertical integration on a scale nobody had attempted before, and it worked spectacularly. The numbers from this era are staggering. In 1860, the average American blast furnace produced about 3,500 tons of pig iron per year. By 1900, that number had jumped to 38,000 tons per furnace. That is not a gradual improvement. That is a 10-fold increase in 40 years. And it was not just about building more furnaces. The furnaces themselves got bigger and more efficient. In 1850, a typical blast furnace stood maybe 40 feet tall. By 1880, they had reached 70 feet. By 1900, they topped 100 feet. American ironmakers were also pioneering the use of coke instead of charcoal, which burned hotter and allowed for bigger charges and faster throughput. They built hot blast stoves that preheated the air before it entered the furnace, saving enormous amounts of fuel. They designed mechanical skip hoists to haul raw materials to the furnace top instead of relying on workers with wheelbarrows. Carnegie was obsessed with efficiency. He hired chemists to analyze every batch of ore and every load of coke so that his furnaces ran at peak performance. He tore down furnaces that were only a few years old if a better design came along, because he understood that a more productive furnace paid for itself in months. His competitors clung to older equipment to avoid the capital expense, and Carnegie buried them on price. The result was an explosion in output that rewrote the global balance of industrial power. In 1890, American iron production surpassed Britain's for the first time. By 1900, the United States was producing 15 million tons of pig iron per year. That was roughly 200 kilograms for every man, woman, and child in the country, and it was nearly 40 times the entire world's iron output from a century earlier. One country, one generation. That is how fast the American blast furnace industry scaled. And then came the deal that turned all of it into a single corporate giant. In 1901, the financier, J.P. Morgan organized the merger of Carnegie Steel, Federal Steel, National Steel, and 7 other companies into the United States Steel Corporation. Morgan paid Carnegie $480 million for his share, a sum worth over $13 billion in today's money. U.S. Steel was capitalized at $1.4 billion, making it the first billion-dollar corporation in American history. In its first year, the company controlled roughly 2/3 of all steel production in the United States. It owned the mines, the railroads, the ore boats on the Great Lakes, the coke ovens, the blast furnaces, and the finishing mills. It was, by a wide margin, the largest industrial enterprise the world had ever seen. If you are finding this useful, take a second to hit subscribe. We cover stories like this one every week. The real test of this industrial machine came during World War II, when the United States entered the war after Pearl Harbor. In December 1941, the nation's blast furnaces became the beating heart of the war effort. The government and the steel industry had already been ramping up production under the National Defense Program Act of 1940, U.S. Steel doubled its output of raw materials, built new blast furnaces and open hearth furnaces with government subsidies, rehired retired workers, and pulled obsolete equipment back into service. Employment at U.S. Steel alone jumped from about 254,000 in 1940 to a wartime peak of 340,000 in 1943. The output numbers tell the story. American steel production surged from 67 million tons in 1940 to a record 86 million tons in 1944. Every tank rolling off the assembly line required roughly 18 tons of steel. The country built around 300,000 military aircraft during the war years: battleships, destroyers, aircraft carriers, landing craft, artillery pieces, ammunition casings, railroad track, bridges. All of it started as iron ore dumped into the mouth of a blast furnace and came out the other end as liquid metal ready for the steel-making furnaces. The civilian economy was stripped bare to feed this machine. In 1941, American factories had produced about 3 million automobiles. During the entire rest of the war, the country manufactured only 139. Every other scrap of steel went to the military. The blast furnaces of Pittsburgh, Gary, Birmingham, Youngstown, and Bethlehem ran around the clock, their glow visible for miles against the night sky. Ore bridges at plants like the Carnegie, Illinois Works in Farrell, Pennsylvania, carried enormous loads of raw material to what the wartime propaganda posters called the hungry blast furnaces. Workers pulled 12-hour shifts in heat that could peel skin from 100 feet away, tapping rivers of molten pig iron every 3 to 5 hours in batches of 300 to 600 tons at a time. The iron poured through sand channels in the casting house, a blinding orange-white torrent throwing off sparks and radiant heat while overhead cranes swung ladles the size of small buildings into position. The Republic Steel Furnace in Warren, Ohio, which had been completely rebuilt in 1939 with a larger Bosch and taller stack, was churning out over 400,000 tons of iron per year at its wartime peak. Bethlehem Steel was running flat out from 1863 all the way through the end of the war. This was not elegant work. It was loud, dangerous, and relentless. Men worked in conditions that would shut down a modern factory in minutes, but it was the industrial engine that won the war. After the war, domestic demand only grew. Millions of returning soldiers needed houses, and the GI Bill put mortgages within reach for families who had never owned property before. Suburban developments sprawled outward from every major city, and every one of those houses needed steel nails, steel pipes, steel appliances, and steel-reinforced concrete foundations. The interstate highway system, authorized in 1956, required millions of tons of reinforcing steel for bridges and overpasses stretching from coast to coast. The auto industry roared back to life. Consumer appliances, from refrigerators to washing machines, flew off the lines. All of it demanded steel, and all of that steel started in a blast furnace. By 1953, U.S. steel alone hit a production peak of 35.8 million tons. American steel capacity reached 154 million tons annually by 1962, nearly double wartime levels. The blast furnace had become so central to American life that the glow of the steel towns along the Monongahela and Ohio rivers was simply part of the national scenery, as ordinary and constant as the sunrise. Today, a modern blast furnace is one of the most impressive machines on the planet. It stands over 100 feet tall, with a hearth diameter that can stretch to 50 feet across. At the combustion zone near the bottom, where the preheated air hits the coke, temperatures exceed 2,000 degrees Celsius, hot enough to melt virtually any material on Earth. The furnace eats raw materials at a rate of about 100 kilograms per second, a continuous flow of ore pellets, coke, and limestone descending through the shaft while superheated reducing gases rise through the gaps. A single large modern blast furnace can produce more than 10,000 tons of liquid iron in a day, enough to fill roughly 30 Olympic swimming pools every week with molten metal, and it does this without stopping. Once lit, a blast furnace campaign runs continuously for a decade or more, tapping iron and slag at regular intervals around the clock, 365 days a year. The only time it goes cold is when the refractory brick lining the interior has finally eroded to the point where the entire furnace must be gutted and rebuilt from the inside, a process called relining that takes months and costs tens of millions of dollars. The slag that floats on top of the molten iron is tapped separately and cooled into a volcanic-looking rock that gets sold as fill material for road construction. The blast furnace gas that exits from the top, a mixture of carbon monoxide, carbon dioxide, and nitrogen, is captured and burned to preheat the air stoves or generate electricity elsewhere in the plant. Nothing is wasted. The entire system is a closed loop of chemistry and thermodynamics running at the edge of what materials science will allow. And here is the part of the story that most people forget. The iron that comes out of a blast furnace is not steel. It is pig iron, and it is full of carbon, around 4 to 5% by weight, which makes it hard and brittle and useless for most structural applications. To become steel, that pig iron has to go through a second process, usually a basic oxygen furnace, where a lance blows pure oxygen onto the molten iron at supersonic speed, burning off the excess carbon and leaving behind a metal that is stronger, more flexible, and endlessly workable. The blast furnace does not finish the job, it starts it. It performs the brutal first act of ripping oxygen away from iron oxide and delivering a river of crude liquid metal to the next stage of refinement. Everything that comes after, the steel beams in your office building, the rebar in the highway overpass, the body panel on your car, all of it traces back to that moment when a blast of superheated air hit a bed of burning coke and the chemistry of reduction turned dead rock into living metal. The American blast furnace industry is not what it was at its peak. Electric arc furnaces, which melt recycled scrap steel using massive electrical currents, now produce a growing share of the nation's steel. Companies like US Steel have invested billions in new electric arc furnace facilities, and the proportion of steel made from scrap has climbed steadily for decades. Overseas competition from Asia, especially China, has reshaped the global market in ways that nobody in Andrew Carnegie's era could have imagined. China alone now produces more steel in a single year than the United States produced at the absolute height of its dominance. Many of the great steel towns of Pennsylvania and Ohio have gone quiet, their furnaces torn down or left standing as rusted monuments to a different era. The Monongahela and Ohio River valleys, once lit orange every night by the glow of molten iron, are darker now. But the blast furnace itself is not gone. It still operates in Indiana and Alabama and Illinois, still eating ore and breathing fire, still doing what it has done for nearly 4 centuries on American soil. U.S. Steel's Gary Works in Indiana, built in 1906 on the shores of Lake Michigan, still runs blast furnaces today. The fundamental chemistry has not changed since those first workers at Saugus loaded charcoal and bog ore into a stone shaft and pumped bellows powered by a water wheel on a Massachusetts river. Carbon still reduces iron oxide, slag still floats on molten metal, and the iron still pours out glowing at the bottom, the same way it did when this country was 13 colonies clinging to the Atlantic coast with nothing but an ocean behind them and a continent of raw material in front of them. From a muddy riverbank in Massachusetts to the largest corporation the world had ever seen, from a colonial furnace making cooking pots to industrial giants producing 10,000 tons of liquid metal a day, the blast furnace did not just make iron, it made America. If this video taught you something new, drop a like and subscribe to the channel. And tell us in the comments, what other industrial process should we cover next?